Okay, can you hear me fine? Because all I can do is hear myself. So, all right. My name is Andrius, and today's session is going to be about using Apache Kafka for modernizing OpenEdge applications. And to start off on the right foot, so there are a few facts about me. I am living with OpenEdge near my heart since the beginning of 2020. I have experience in banking, medical billing, and simple data administration projects. I am also curious about third-party integrations, and my main passion is cars and driving them. And as you can see from the picture, I do not actually enjoy fixing them. Similarly as with the development, fixing things is necessary, and sometimes, the result is just better. So the company which I've come from is called Baltic Amadeus. So in a week, it's going to turn 35 years. We have over 250 IT talents, and we have projects all across Europe and outside, across the Atlantic Ocean. And since POG is about the Progress OpenEdge, well, really, so our Progress unit is working with Progress since 2003. We have over 40 specialists and are still growing. And we are pretty young and at the same time experienced as well. You can really recognize us by these white t-shirts. If you want some of them, we have them by our stand. And we have experience with mission critical and legacy systems or ERP systems. And mostly our work is related by helping customers with support, new development or modernization projects. And we are used to be working with all major frameworks for Progress OpenEdge. So that is for our short introduction. So our agenda for today is, first I'm going to do a very short introduction to modernization. Then the main meat and potato section would be proof of concept research and development, where we are going to look at how we have developed this proof of concept using Kafka. Then I'm going to show you a quick demo, what have we achieved, and then we will move to conclusions. So without further ado, a short introduction to modernization. So now you might be wondering, why should anyone modernize? Well, according to the survey by the Newstack from the last year, there are few reasons mentioned here, but there could be countless reasons. So for example, you would like to increase reliability, improve security, increase scalability. There could be multiple reasons, but the main and probably most important reason is that the legacy application is limiting you in some way. Maybe the code maintainability is difficult. So let's just say you decide to modernize, and generally you would have two approaches. Well, it could be more, it could be with more niche specifics, but generally there are two approaches. So the first one is the Big Bang approach. It's where you develop the modernized application. It's finished, you just put it to the production, shut off the legacy application, and everything is fine. That doesn't happen usually, unless the application is relatively small. Then of course the business requirements do not change that often. Sure, the approach would save you time, so you don't have to do any infrastructure changes when developing the software. However, the more safe approach is the incremental modernization approach. It's where you just modernize the application bit by bit. So it's a gradual modernization, and you can shut off the legacy application data streams or some functionality modules in blocks. So this session is more about the second approach, and now we can move on to our proof of concept research and development. So to start off, the main research idea was to imitate the modernization scenario, where we would take the legacy application and gradually modernize it to be something more up to date. One thing worth to mention here is that we are talking strictly about applications modernization. We are not taking into account the any infrastructure changes, just to keep things simple, because we wanted to try things out with Kafka. And moving on with the main goal, well, as I briefly mentioned already, the main goal is to research the possibility in using Kafka in such modernization scenarios. And of course, to research about what are the limitations for OpenEdge, since Kafka is widely supported by multiple technologies, and what adjustments had to be made specifically for OpenEdge. Now, the research strategy, initial research strategy had 3 stages. So the first stage was the start stage, obviously, nothing really fancy naming here, but that was the implementation of one-way data flow from legacy to the modernized side. Really simple, specifically mentioned here for one table. So we had really 2 small mocked applications, and we wanted to see whether we can deliver the changes from the legacy side to the modern side, so just like a data flow. If we succeed in doing that, then of course the add stage would come up, which is just simply the addition of the remaining few tables. In theory, it should be just copy-paste. And then the last stage is the complete stage, and it is the implementation of a 2-day data flow between applications, since this is a gradual modernization, the incremental one. So you might be working on the modernized side on some functionality which is still working fine on the legacy side. So you would want to be able to synchronize the data between the 2 sides, so you avoid any data conflicts. Now, about the legacy application, it is really simple. It is based, its UI is based on an ADM framework. Really simple, really early 2000 style. It only has 5 tables, really simple CRUD operations, and it currently runs on OpenEdge well, not last, the 11.7 LTS version, which is ending its support, the first of all of the LTSs. Similarly, as for the modernized application, it's again simple CRUD operations, nothing too fancy, running on the currently latest LTS version, 12.2. 6 tables, so 1 more table, just to see if we could stream from the legacy to the modern side into 2 separate tables. So we have 1 source table and 2 target tables. And it is just same application, just with the fancier UI. So we have, and of course, we have PassWe with the web transport, and of course, we have Node.js like a middleware for the front end. And since this application is about Apache Kafka, well, I'm going to do a very quick introduction to that. So as probably all of you know, Apache Kafka is open source distributed event streaming platform, which is easily scalable, and it is supported by multiple technologies. And just by coincidence, it's supported by progress from version 12.5. By supported, I mean it Progress provides us the libraries to use for creating our own consumers and producers. And since I just mentioned those 2 buzzwords, I guess we can move on to this slide. Now, this is really a simplification of how Kafka operates, but it gives us a pretty good idea to understand how we were thinking in this proof of concept. There are 3 parts. There is a producer, Kafka broker, which contains topics, and there is a consumer. So the producer is just a piece of code which writes the data to Kafka topics, then the topic or the whole broker is kind of responsible for accepting the producer's requests and giving out the information to the consumers. And as have you probably already understood, the consumer is the part of the code which actually accepts the data, and then based on the data, it can be manipulated. So it may be validated, it might be written to the database, and etc. Now, the initial modernization strategy is really simple. It will change over time as we move on through our story, but basically there are two applications, so the legacy and the modern, which have their separate legacy and modern DBs, which are on the different versions. So legacy is on 11.7 as a reminder, and modern is on 12.2 as of this stage. And we have Apache Kafka at that time a black box. We didn't actually know how are we going to implement, so we would have this as a black box for now, but it will change over time. And the first steps, since we began our development, are more of environment setups. So we had to prepare our initial DF and D files for modern legacy databases mockup. We had to set up our Docker environment. And to actually get the data which we need, we decided to use Change Data Capture, or CDC, which is available from Progress version 11.7, if I'm not mistaken. Yeah, it would be 11.7. And again, since we didn't have any previous experience in working with Kafka, not to mention with the OpenEdge, we had to start from the basics. So we had to research about how OpenEdge and Apache Kafka should communicate, and we decided to use JDBC connections, since OpenEdge databases like JDBC connections, and Apache Kafka just loves them. So we decided to go with that. Additionally, we decided to use Confluent Kafka instead of only Apache Kafka as a vanilla version. So the only difference between these two is the Confluent Kafka is a more commercialized version, and it actually provides pre-coded connectors that we can use specifically for sending the data across Apache Kafka, so we wouldn't have to do any additional coding. So since the community actually provides us, but Confluent Kafka has the commercialized versions, so we can just pick up these connectors and just use them by just changing the configuration file. We wouldn't have to do any coding. And eventually, we tried to test the first Kafka topic. So it was really simple. We didn't try to do anything with the CDC as of yet. We just wanted to put the information in Apache Kafka's topic. And another change here is Apache Kafka Connect. As I probably missed to actually show you the change, but Apache Kafka has a component, Apache Kafka Connect, and we decided to use specifically Apache Kafka Connect because it helps us to stream the data specifically between the two databases, or more databases even. And it is as I mentioned, a component of Kafka, which kind of serves like a centralized data hub. And it actually provides you to transform the data into the required formats. For example, this site could be not an OpenEdge database, but an SQL database. So there is a ability to transform the data inside the Kafka Connect. But generally, it is used for connectors creation and coordination, and of course, moving really large data sets. We didn't test that because our database is really small, but it can be used for that as well. So how our diagram has changed? Well, we still have the same Kafka topic, except we have Kafka Connect's source connector, which initially was used for initial data transformation. So we got the data from legacy database, and then we would transform it into the specific JSON format because Kafka actually expects to have it in a very specific format. Otherwise, it would just give us out some pretty nasty errors. And the sync connector is used for just taking the data out of the topic and just writing it to the modern DB. Now, this solution, if it would work, we wouldn't have to do anything from the ABL side, so no coding involved, which sounds like a match made in heaven. However, we had to drop this idea since the deletion only works when the null value with the non-null key is passed to the connector. So this part, we could work something out in the team. However, the upsert mode, which was necessary for deletion, since the connector didn't have any delete mode which would work for us, upsert mode was not supported by OpenEdge database generic dialect, and we tried multiple dialects in the connector's configuration file, but we couldn't get it to work. And again, there were some strict limitations on what can be customized, since remember, this is only a configuration file. We couldn't access any code, so we couldn't do anything very custom. And eventually, our decision was to just drop the sync connector altogether, and well, we kind of are left with the blank space over here. And inside the team, we were discussing how we should move further, and eventually decided to use the client consumer, and that meant that we would need to use the OpenEdge libraries. And well, we decided just to update the modern application to 12.6. And as we know, 12.8 is coming out sometime in the Q4, hopefully. So it will have Kafka libraries as well. So it would make sense just to go with the newest version in most cases. And of course, we had to reduce our CDC tracking level to 0, which means that we would only take, not only take, but the CDC would capture the changes if at least one field has changed. So let's just say the first name has changed, it goes to the CDC, and we would just change the whole table for the target table, for the target database table, sorry. And we wouldn't care if only the specific fields would change, as it was with the previous tracking level. Now, if we would move on, this is a really brief example. How do we fetch data from CDC? So we have two systematic tables or schema tables, however you want to call it. And we have CDC change tracking and underscore file table. So in CDC change tracking, we are storing the source table number, which we can get the table name from this underscore file table. And this is one of the tables which is being used by the application. And by doing this, we can actually get the right records each time, and just to fetch them from the CDC, so can write it to the target database. Now, of course, nothing is perfect even with this solution, but these are pretty small things which we found our way of working it out. So as one of the things, the correct placing of OpenEdge jar file, which without that the JDBC connections would not work. So we had to place the OpenEdge jar file in a very specific location. Otherwise, the Confluent Kafka would get really mad, and it wouldn't work at all. The other things were for the query writing, the characters underscore or the dashes can cause issues when writing the Kafka JDBC connector query. So we had to do some escape adjustments. And again, in incrementing mode, so the connectors have their own modes, but we were using the incrementing mode. The connector has to be able to append its own where clause, which meant that inside the main query, we couldn't write any where clauses, but in the subqueries, we could. But again, this was not an issue, just a neat little finding, which we found out. Well, it looked like it's a light at the end of the tunnel. So we successfully did a test run to update the record from legacy to modern application. And the next steps were of course, the addition of remaining tables to the mix. We also had to put additional, actually research additionally on how to synchronize the data between the two applications. So what is the standard for that? Are we actually talking about good approaches to this? So we wanted to research how other modernization projects could be implemented, and we kind of read about whether our solution does make sense, basically. And of course, we had to do some little adjustments for the delete functionality, which I'll show you just about now. We decided to use one more field to each of databases tables, which is called in the modern database it's called legacy row ID, and in the legacy database it's called modern row ID. And for this, this is really important because as it is shown right here. So let's just say that delete occurs on the legacy database. So from the applications database, applications table, the record is gone, but the CDC actually captures the change. However, the problem here begins where we actually try to query the data from the Apache Kafka from the legacy DB with the given row ID. And we can see that this record does not exist, and we cannot get the particular row ID only from the CDC table, and we cannot make the deletion on the other side. So we cannot get from the applications table to send it over to the modernized DB, and it would happen that the legacy DB has the record deleted, but the legacy DB still has it because we do not know which record to delete. So in using the legacy and the modern row ID, we could actually get it because we get the row ID and we can compare it with the legacy row ID when the record was synchronized between these two databases. So we can take the row ID from the CDC table, we can send it over here, and we can compare it. And the deletion actually only looks at the row IDs. So we can find the exact record, and the deletion can be completed. Then the additional new implementations. So yeah, we finished the delete. So since all operations like delete, update, and create were working fine, we decided to move on with the two-way streaming approach, and that meant that we have to use the Kafka libraries again, so we had to upgrade the legacy application version to 12.6. And again, we had to think of a CDC enable and disable functionality to avoid looping of data. How it works is pretty much shown here. So let's just say that the legacy app has an update statement. Then the update statement goes to the modernized DB based on the CDC changes. The modernized DB updates the data, but it writes itself to the CDC table again. And then, since CDC tracks the change, it goes again to the legacy DB. Legacy DB does the update, sees it in the CDC table, again sends it back, and the constant loop just doesn't end. So the way which we did was we had to enable and disable the CDC only if the request was made in the consumer programs. So each of applications have only one consumer, and if the change comes to the consumer, we just enable, first we disable, do the changes, then re-enable the CDC, because we need CDC to be able to track the changes which are made in the application, not from synchronizing the data from Kafka. And the final solution pretty much looks like that. It's a bit more items on the diagram, but it's pretty much the same. It's just these are copy-pasted over there. So it's looking a little bit bigger, but most probably important part is that the client consumer, which was written in the ABL on each of the sides, actually it is written in the dynamic way, so it can accept the changes for all of the tables. So it is dynamic. It doesn't matter which table there is, and of course there are each topic is responsible for one table, and of course there are 6 source connectors on each side. Okay, so since I've talked a lot, I would really like you to show how it works. So let's move on with the demo. Let me see. So let's just say we have the modernized application, and then we would have the legacy application, which I'll just move this. And oh boy, okay, I thought this window was going to be a bit smaller, but okay. So let's just say we have a list of physicians. Really doesn't matter what do we have here, but let's just say we would like to add a new physician, so I can just type myself here. I don't have any middle name. Am I active? Probably I am. Didn't click this. Okay, and then we have some address, city, zip code, and NPI number. And I would just click submit. As we see, the new record is created. If we would go to the legacy application, we have myself as well over here. And these are 2 separate databases. Now, if I would do the update, hello. If we would do the update, let's just say I'm changing my name to John, for example. Then if I would click refresh, we see that the changes, so the updates are coming in, the creates are also working. And what about the deletes? So the delete, let's just say we can use demographics table. So in total, we have 6 records, right? So let's just say I'll do the delete of one patient. Sorry, not the delete physician, not the demo. So let's just say we do, I want to delete myself. So for example, I delete myself, and then the refresh, as we see, I actually disappeared. Now, let's just say in theory that you have finished modernizing every part of physician-related functionality. Let's just say all of your modules are already modernized and you would like to shut off the synchronization for the physicians. So in this way, we have a list of connectors, which is not very well visible, but essentially we have the whole configuration also over here. So you can easily, pretty easily remove them. You don't have to read what is over here, but this is the whole list of each of the connectors. So 6 connectors for modernized side, 6 connectors for the legacy side. So what we need to do is to find the name of the physician. So we have old physician, and we would have physician. So we need to remove these 2 connectors just to stop the synchronization. You do not need to restart the application or anything. I'll just probably move this to the next screen. Okay. Yeah, it's not really clean, but still. Okay, and all you need to do is just delete the connector with the different names. And let's just see, we delete physician from the modernized side, and we had, if I remember correctly, the name for the physician old was old phys. Okay, so that one is for the legacy one. So if we would remove it, then the connector list would shrink a little bit. So there are 2 now missing connectors, and the synchronization is no longer there. So if, for example, I would add myself again, and I am active and I do not have any address. So if we would go to the physicians, you would refresh. As you see, I am not appearing anymore. Similarly, as on this side, I can do the update. So Zaha, and we would add capital S at the end. So we would really see the change. And if we do this, as you see, it is not updating. It should have appeared over here. And yeah, that is pretty much it for our demo. So let's get back to the conclusions. Okay, so to summarize, what went okay? We were pretty surprised that the consumer implementation using Kafka libraries was relatively simple. Of course, we didn't do anything too fancy, but the most probably time-consuming part of the consumer implementation was the actual dynamic queries themselves. From the Kafka standpoint, pretty straightforward, didn't have any problems. When the implementation of the full data flow was done, the other tables addition was quick and smooth. So as I mentioned in the beginning of the presentation, theoretically it should have been copy-paste, and it was. So again, everything went okay. And there were no additional issues when the solution was finished. We didn't encounter any crashes or any lost data unless it was expected, as I've just shown you here when I deleted the connectors. But again, we would probably the testing, since it's just never enough to test of the testing time. So basically, Maybe we didn't spot anything, but this is what we encountered, and the solution worked pretty well. Now, what things needed adjustments? So, yeah, as briefly mentioned before, the CDC activation had to be adjusted for the consumer programs to avoid the loop. The delete functionality meant one additional field of some row ID, so legacy row ID or modern row ID in each of the tables. So if you would add a new table must have this legacy row ID or modern row ID. The startup sequence had to be specific for initial bulk load and the consumer start. This one, initially when we are starting up the environment, we are doing the bulk load. So we have the D files, which are being loaded to the legacy and to the modern side, and these are different. So initial bulk load just basically loads all of the data from each databases for the initial startup, just to have the synchronized data on each database. So the sequence had to be specific because first you have to do the bulk load, and only then you need to start the consumer, so all changes are actually synchronized. And of course, you just need to update the legacy application to at least 12.5 if we are talking about more real-world scenarios, because if you would like to use the libraries, probably legacy application is not going to be that new most of the time. There could be exceptions. And yeah, I would like to express my thanks to the team. So my colleagues, Agle and Paulius, were helping developers, and Arturas Birbulas was our whole advisor to this whole thing. So yeah, that is pretty much it. Thank you. Any questions? Maybe I didn't show you something that you were interested. I'm not sure. Okay. Yeah, so I guess we can have a break. Thank you.